part D.3, Project 2, Problem Size and Performance. First, let us look at item number 1 in the Project 2 description. That is, determine an appropriate problem size for the first method. We know the first method is very slow. So when you run it, after you enter certain problem size, you can notice it takes quite long to give you the answer. Yeah. But here, in this first step, we want to look at the relationship, the problem size and the response time. So these two things for the first method. All right. Relatively large size. Here we do not have that idea, right? How large is the size? So we need to determine an appropriate problem size. So what's the appropriate? I set some criteria. I set some reasonable criteria. So for you to just get that approximate problem size. Now, in our first program, we will pass the problem size, that is the number n for the Fibonacci number Fn. There are 3 ways you can choose. Now, how do you pass problem size? Here, in this description, I give you 3 possible ways you can use. The first way, command line input. When we use Eclipse IDE, so this way, although we can set, but it is not convenient. It is not very convenient. Although you can set, so before you run, click the run button, then you need to configure before you run it. In that configuration window, you need to select there is an argument tab. You need to select that, enter problem size number, and in your method, in your program, you need to retrieve that argument value and use it. Yeah. That way is not very convenient. So most of the students, they do not like to use this way. Yeah, based on my experience, they do not like to use this way. Yeah. For me, myself, I do not like this way. So I give you other options. Yeah. So you can choose other options. The second option, prompt for input, right? Yeah. So that way, prompt for input. Yeah. Many students like this way. Yeah. Prompt, print out a message. Yeah. After that, the user enter problem size, enter, then you use some special way to read the input number, so then you do the remaining processing. Yeah. That way, many students like this way. Yeah. So number 2 way is also okay. Number 3 way, I also allow you to do that. Hard-coded way. All right? Hard-coded way. So it's okay. In your program, you have a variable, integer variable for that n, problem size number. So you just type n equals certain number, save, then you run it. Yeah. That way is the simplest. Although the hard-coded way for our computer science people, most of the time we like to avoid it, right? Yeah. So I understand that. Most of the time we want to avoid hard-coded way to set parameter values. Yeah. But here, because our main focus is not on that, our main focus is on other important aspects. So we don't worry about this convenience, good or bad for this particular little thing, right? So I allow hard-coded way because convenient, right? Yeah. All right. So next, right after that, record execution time. Yeah, I think you can search the web to find how to do it. Yeah, before you so here you set 2 points. Like stopwatch. Okay, stopwatch. You calculate the difference between 2 particular points. First, you start looking at the current time in milliseconds, yeah, nanoseconds, right? Yeah, based on the method you use. Yeah. All right, then you call the recursive function after that. Yeah. Then after you get the result, at the end, you check your clock another time. Then you take the difference of those 2 numbers. So print out, yeah. Because the nanoseconds, that time unit, too small. So usually we have very large number. So probably the milliseconds, that time unit, more reasonable. Yeah. But when you increase the problem size, that number becomes bigger and bigger. Yeah. So you play around. Yeah. Here I can let you know the number you do experiment for this part should be less than 100. Well less than 100. Otherwise, you may have problem. All right. Yeah. So here I just give you some sense. If you put a very big number, then you will wait forever. You won't get anything. You will wait forever, right? Yeah. So try to control, less than 100. Yeah. At the beginning, put some relatively small problem size numbers. Yeah. And see how long you need to wait. All right. Next, when you do experiments, find the problem size n0. Here, define this n0. Here we want to set a particular point. So let people feel about it. This special problem size. So what is the criteria I want to use here such that your execution time f sub n0 is approximately 30 seconds on your machine. Approximately, not necessarily exact. A little greater or little less, it's not important. Just close to 30 seconds. Okay? Yeah. But you will feel waiting for 30 seconds when you run a computer program. It is extremely long. 30 seconds will be extremely long in our, common experience. We feel so long. We don't expect such a long time. Yeah. So here I use that. Yeah. Before I used 60 seconds, even much, much longer. Yeah. But for this semester, I want to reduce that because 30 seconds already long enough. And let us just take the 30 seconds. Yeah. All right. Right. So then you print out message on screen. Yeah. So when you run the program, just print out that n0 number because I want to see on your particular machine, right? So here on your machine, on different people's machine, that appropriate problem size usually different. So I want to see on your machine, how big is that number? Some people have faster machines, some people have slower machines. So that number should be different. Yeah. All right. Yeah. Okay. Yeah. So, right. So in half a minute. All right. So then in order to avoid overflow, yes, Fibonacci numbers are increasing very fast, very, very fast. Yeah. So then, sooner or later, you will have an overflow problem. Yeah. So if you start with integer data type in Java, here I use Java as an example. Yeah. We know in Java, integer data type, 4 bytes, right? 4 bytes. 32 bits, right? How large it can be used depends on signed or unsigned, right? Yeah, signed or unsigned. Yeah. But even it's large or small, the maximum it can be used to represent 2 to the 32 second power minus 1, right? The largest possible integer value it can be represented. But this number is not that big, right? So you can get an overflow easily. So for that reason here, I recommend you use long integer type for this step, because in that way, you will have 8 by integer, right? So that will be 2 to the 64 minus 1, maximum number it can represent. Yeah. Let us assume unsigned, right? Because unsigned you can do bigger. Yeah. Signed, half, right? Cut that number by half. 1/2 at the positive side, 1/2 at the negative side. But here we want to put all the numbers we can use at the positive side. So we can do much more. Yeah. Yeah. But whatever it is, for this step, your processing limit is significant. Your processing limit is there. Yeah. So not that big. You cannot go very far. Yeah. So then we will have following steps. So we can do more and more, faster and faster. The problem size processing, we have the capability to process bigger problem sizes. All right, so let us complete our DPON 3 video right here. Yeah.